Good afternoon, everybody. Stefano Cei here from Peralisi. Can you hear me, all of us, all of you? Okay. I'm the Chief Technical Officer here in Peralisi. I'm with Riccardo. Riccardo is part of my department, and we will introduce to you the Ultrasound project today, together with the other partners who are collaborating with us. Paolo, next, please. Okay, the first point that we will see, we start defining the market needs and reviewing also the product industrialization of this Ultrasound project. This project is part of the Fast Track for Innovation. And let me introduce what is the Fast Track for Innovation project in the next slide. Fast Track for Innovation is a funding program for proposals starting from for bottom-up proposals close to market for close to market innovations in any area of technology or application. In the next slide, I will give you more details about this. This project is part of the Horizon 2020 Fast Track for Innovation program. This approach is based on a technology readiness level steps, moving from the one, which is the concept, going through every validation step, arriving to the TRL9 level, which is the final product close to market. Just to give you an overview of the importance of how this project is important and how, let me say, challenging is this one. This type of approach is applied on every technology, on every innovation, and as a very small acceptance level, around 5%. This is a very good demonstration on how the teamwork that we have used within all the other partners has gone well, and how the showing us and putting together excellences from all the European countries. This kind of approach is moving with this bottom up, and as the challenge to arrive to the final project within 3 years from the concept till the final commercialization. Paolo, can you move to the next slide? Let me introduce the project partners. Just give me 1 second. I would like to say that this is not only the description of a project, but also a journey that all of us have done during this project. And this is the reason, because you will see the partners alternating during this discussion, this presentation, because I think it's very important not only to see the project, but also to demonstrate the collaboration and that has been established during all, the entire project, and so that every partner can introduce the challenges and the tasks performed over the entire project. Peralisi is the first one, since Peralisi is the coordinator of this project. But in this project we have 5 partners: CITIC-SITA, which is in Spain; Almazara del Ebro, still in Spain; Cedrat Technologies is in French; and then Peralisi and Università di Bari, for sure, in Italy. As you can see, the amount of money invested in this project is pretty high. We talk about around 2.5 million euro, and the European community financed around 1.9 million euro. The project started the 1st of January 2019. The closure had to be at the end of 2020, but due to COVID reason, we got the exception from the European community to postpone it 1 year to arrive to due to the restrictions in testing and traveling all around Europe that we had last year. Paolo, next, please. This is an introduction about Pieralisi. Pieralisi is the coordinator, and Pieralisi is one of the leading players for the supply of centrifugal separators and extraction solution for different applications. We move from environmental, food and beverage, recycling, mineral fuels, lubricants, chemical, pharmaceutical, animal byproducts, and more and more. And we are still working on extending our applications. Paolo, please. Next. Okay, next one. We have Pieralisi as an extensive experience in the olive oil industry, and we are the leading company, the leader in the supply of continuous cycle plants worldwide. For sure, our targets are the customer satisfaction for today, and for sure more and more in the future. Pieralisi is able to provide a complete production line or single machines, and please consider that we invest the yearly lot of money to increase our competitiveness and output, and also improve the performances of our machines, both single machines and entire production line. We have around 40,000 machines installed worldwide. We have around 500 people and under 30 technicians that are dedicated to machine and plant configuration, after sales, and services. Worldwide, with worldwide distribution, for sure, olive oil as a more as a wider, let me say, extension and intensive after sales presence. Paolo, please, next. Okay, we just last one about Pieralisi. Last slide about Pieralisi presentation. We have for engineering approach on all the machines, and all the machines are. I'm talking about, when I'm talking about machines, I'm talking about single machine, and multiple machines or entire plant. All of them are designed and produced from here, from our headquarters in Jesi, where we train our technicians for commissioning and maintenance activities. And we work according to the circular economy principles that are part of the 2030 roadmap. We have a lot of patents in both food and beverage and environmental machines, and this is the evidence of our commitment in research and development of new technologies worldwide. Okay, let me introduce the olive oil, the Ultrasound project, and the innovations that we want to pursue in the olive oil sector with this machine. Please, next one. Okay, if we consider an entire olive oil plant done by multiple machines, from the washing machine till the vertical separator, we have this should be, or is aimed to be, a continuous production plant where we have the bottleneck in the malaxation process. The malaxation is in this small picture are the three machines on the right with the yellow box malaxation, and it is a point where a point of accumulation of olive oil paste, and this is, as I was saying, the bottleneck between washing and crushing and the separators. And this is, and it is the limit in terms of capacity and continuity of the entire plant. And this is the reason because we decided to develop, together with all the other partners, a technology allowing to move to a continuous extraction process, to able to reduce the process time, increase the yield, and but also maintaining and maximizing the extraction capacity in terms of phenols, maintaining the temperature under control. All of that to allow to maintain the sustainable process consistent with the roadmap of 2030 agenda. Now I think it's the time to have Maria Lisa introducing their part.
Hi Stefano, thank you very much. I ask to the organization to control the presentation, please. I need to share my screen. Okay. Well, good afternoon. My name is Maria Lisa Clodoveo, and I am Associate Professor of Food Science and Technology at the University of Bari in Italy. So, in about last 50 years, virgin olive oils technology has evolved by transforming the discontinuous extraction system based on pressure to modern continuous system that use centrifugal force. Well, despite the huge progress, it's still now possible to obtain the maximum virgin olive oil yield and the maximum product quality simultaneously. I think that it is necessary to develop an innovation able to break this historical paradigm. So, an innovative olive oil device should help to obtain a soft break of the cell passed intact through the crusher, favoring simultaneously the following action. 1. Avoid emulsion and temperature rises. 2. Accelerate the coalescence phenomena of little oily drops. 3. Allow the dissolution of biophenols in the oily phase. 4. Increases the synthesis of pleasant volatile compounds. 5. Limit the oxidation of fatty acid and polyphenols. 6. Finally, realize a system that effectively operates continuously. If we look at the current system of extraction of extra virgin olive oil, it is clear that all the machines upstream the malaxer operate continuously, and all the machines downstream the malaxer operate continuously. The malaxer is the only discount machine in a continuous system. So the malaxer represents the bottleneck of the process, and the current solution consists in multiplying the number of the malaxer. Ultrasounds are the best solution to overcome this problem. Okay, but what are ultrasounds? Ultrasounds are sound waves with frequencies higher than the upper audible limit of human hearing. Thanks to ultrasounds, we can have cavitation. Cavitation is a physical phenomenon consisting of the formation of vapor bubbles that, after their creation, can implode, producing strong shock waves. Now you can see the action of ultrasounds on olive oil cell. Olive oil fruit cells. So, if implosion occurs near the cell walls of crushed olive fruits, it generates the liquid microjets that breaks the wall, freeing the cell contents, so extra virgin olive oil and polyphenols, in few microseconds. The first results of the research was defining two important key factors for the design of the industrial plant. The first one is to define the frequencies most suitable for an effective cavitation. So we choose around 20 kilohertz. The second one is to calculate the specific energy necessary to achieve desired effects in a sustainable manner. The physical value necessary to transfer the results of lab tests made for the first time in the world at the University of Bari in an industrial plant was the specific energy, defined as the quantity of energy transferred per kilogram of olive paste, calculated as the product of the power for the time related to the mass of olive paste. So now you can see in a few seconds all the steps of our research activity that in few years has been transformed in the biggest result of Olive Sound project. The industrial full-scale plant based on the simultaneous combination of ultrasound technology and heat exchanger for the improvement of extra virgin olive oil yields and polyphenols content. Before starting with the technical design of an innovative device, a numerical study combining the simulation of pressure transient induced by the sound waves through the olive paste with the fluidodynamic phenomenon was conducted by the partner University of the Bari. This type of approach helped to define the area of propagation of ultrasound waves with which effective cavitation phenomena were realized. It helped to define the dimension of the effective propagation area of sound wave in order to define three different aspects of the geometry. First one, the thickness of the olive paste completed invested by the ultrasonic treatment. Second one, the minimum distance of the steel walls in front of the ultrasonic transducer. And finally, the third, the minimum distance between two transducers to prevent overlapping of the effective sonication areas that could reciprocally neutralize the effect or cause damage to the transducer. So the results of the simulation is an innovative geometry for the sono heat exchanger, the first prototype made inside the Ultrasound project. You can see now the pressure field analysis that demonstrate that an effective cavitation phenomena occur inside the sono heat exchanger. In this second slide, you can see surprise in surprises, because numerical simulation has highlighted that ultrasonics waves impress a sinuous movement to the olive paste. Therefore, in the industrial phosphate plant, based on the simultaneous combination of ultrasound technology and heat exchanger for the improvement of extra virgin olive oil yields and polyphenols contents, we demonstrate that we have a gentle, a soft breaks of the cell passed intact into the crusher, releasing virgin olive oil and polyphenols, and we have also a slowly mixed of the olive paste, favoring the coalescence phenomena of the oil drops in larger drops, more easily separable in a centrifugal field. Now I'd like to thank you for the attention. A special thanks to my friends and my colleagues Filomena, Corbo, that worked at this project, and it's the time for the presentation of Alexander Page, the CEO of the company Sedrat. Thank you again.
Thank you, Maria Lisa. I will ask Paolo to display the presentation again. Thank you very much. So yeah, my name is Alexandre Pages. I'm a business engineer at Sedrat Technology. Today I would like to present to you the work done by the project team in ultrasonic design, manufacturing, and testing of the transducer. Next, please. So let's have a look to, let's present the company first. We are based in Grenoble, in France. We are an engineering company specialized in mechatronics. So what is mechatronics for us? We provide our customer with actuators and sensors in order to provide mechatronics and detection functions. So we do have cost products, standard products, but we also provide custom through engineering and research and development. The heritage of Sedrat comes from the aerospace industry, and today we spread this knowledge and this innovation to other markets like manufacturing, optronics, and instrumentation. In terms of the product we are developing, you have an overview on the right bottom corner of the actuator. So basically, we develop magnetic actuators in blue, so we can achieve 10 millimeters up to 1 kilonewton of force with magnetic actuators, and with piezo actuators in gray, we can cover a range of 1 millimeter of stroke up to 10 kilonewtons or 10 kilohertz. Above those 10 kilohertz, there are ultrasonic transducer. And this is my next slide. So this is example of what we custom design in the past in the next slide. Paolo. Thank you. So you've got here example of the magic of ultrasonics in other application. Basically, the general effect of ultrasound is it helps the process. It helps in several ways, and here is not a full exhaustively, so what you can do, but just example that Serrat faced in the past with custom design. So we saw very good benefit in injection, in drilling hard to machine materials, also to help reducing the friction in steel casting. In extrusions as well, we have a lot of benefits. Basically, like in this project, we can jump from batch process to continuous process by using the magic of ultrasound. So Cedrat has several patents in transducer design. Every time we design a transducer, it's a custom one, let's say. Let's jump to the transducer that we develop in this project. So that's the next slide. So yes, another one. So that's the first phase before manufacturing the transducer is to first design it. So if you have a look to the concept on the next slide, please. You can see that the transducer is a plate transducer because, as Maria-Lisa said, the plate transducer is the concept chosen in this project. So they are arranged in a plate, and the energy is transferred to the reactor through ultrasonic transducer. So here you have an animations, because the first thing we do in simulation is a model retrofit. We check that what we are going to introduce in the reactor is what we are on the computer. It's easy because after that, we can check the directivity. That's the middle curve, the middle figure that you can see. No, back, please. We can check the directivity. We can check also the acoustic energy transfer with the transducer. And also, we can check how we're gonna attach the transducer onto the reactor, because the way we integrate it has different effect on the pressure and the efficiency. Next, please. So, main conclusion about the simulation is that we are capable of fitting the model. So we've got good reliability, good relevance of the tests, and modeling, less than 3%. We also could see that 28 kilohertz is a good frequency for directivity, power, and coupling. Also, in terms of how we attach the transducer onto the reactor, the flush method, we'll see that after, is the good one. And also simulation helps to design the test bench, because with ultrasound, it's difficult to know where to put the sensor to check the acoustic power, where to check the position. So the simulation helps located where we can stick one or two sensors. Next, please. That's now, I would like to talk about the design of the electronic that gives the energy to the transducer. So next, please. In this project, we wanted to improve the state of the art by what we call the US 2000 power electronic. Why 2000 is just because of the RMS power we can provide in what. So this electronic is capable of providing piezoelectric electricity power in order to cover a very wide range from 20 to 40 kilohertz with a fully controllable panel and digital interface. Next, please. So because of the topology that is inside with PWM and LC filter, it is easy to generate high voltage signal in dynamic with a very large bandwidth. The US 2000 is designed just because it's easy to jump from one transducer to another. It will require very small modification in order to fit one transducer or several transducers. Next, please. An important features of this electronic is the tracking. Something important to notice with ultrasound is that during the process, the temperature will increase with ultrasound. the pass-through or the environment will change in terms of the damping. And also the transducer itself will slightly be modified. All of those three evolutions that we see in the process will make the frequency, the resonance frequency, sweep. And if the frequency sweep and the electronics do not see it, you lose the power. This electronic can lock and track this frequency movement very quickly in order to give the transducer the right level of power at the right time in an efficient manner. So that's the innovation, let's say, and it's combined with also power modulation. It means that we send this 30 kilohertz signal to the transducer, but it is left by a slow signal, let's say a slow sinus. Next, please. So now we have designed the transducer. We have checked it's well adapted to be stick on the reactor. We have the sources, so let's manufacture it and test it. Next, please. So first prototype delivered in 2019 was equipped with a 60 transducer and let's say conventional electronics in order to check that it is possible to send the good power inside the reactor with 60 transducer and 28 kilohertz. I will let my colleague explain the benefit of that in terms of the olive oil yield and over chemical composition that I ignore. Next, please. After this prototype, there were, during 2020 and 2021, the manufacturing integration and test of the scale-up model. So basically, it's 4 vessels. Each vessel is equipped with 60 transducer and a big cabinet behind, as you can see on the photo, will send the power, control it in closed loop, and also display a user interface. Next, please. So how does that work? The power control cabinet will be closed loop with flow rate, temperature, and pressure. It means that according to how the flow rate evolution, temperature, and pressure, and how the user has set the maturity index, the driver will adapt the power needed. So that's how it works. Next, please. So we had to test the different type of transducer. So we had one bench to compare the fixation of the transducer, a second one to test the influence of each transducer together because they interact, they interfere, and this is important to check at the testing level what is the level of interaction together, and also check the boundary condition because the transducer in the middle is not the same behavior as the one on a corner, for instance, and this bench also used to test the brand new electronic US 2000. Next, please. Just a quick view to the bench and testing. So just for you to see that there is not only transducer, there are also a computer, accelerometers, sensors, sonometers, lot of stuff, an example of how we stick, how we interface ultrasonic transducer onto a reactor. Next, please. That's the test of the prototype. That allow us to target the acoustic pressure. So we managed to get 8 bars of dynamic pressure in this prototype. As Maria Lisa said, that's number of bar is enough to generate the phenomena of cavitations. We also validate the power in watt, 6 kilowatt for this prototype, and check that the temperature is acceptable in terms of power dissipation. Next, please. Full system characterization as well. So the full vessels, all the scale-up model was tested as well in similar manner. It was more tested by blocks, but similar value was achieved. between 6 and 8 bars of pressure. Good behavior in terms of temperature. So this scale-up model hits the target in terms of acoustic pressure and power. Next and last on my side, please. So this test bench showed the last characterization of the driver, the US 2000, with a peak power of 4 kilowatts. So this US 2000 was tested at full power, and clearly the cavitation was visible on this test bench. Maybe if we click on the video, we will see the bubbles. I'm not sure. Yes. Yeah. Oh, sorry, that is a codec matter. Anyway, this US 2000 has beaten the record of power in this compared to conventional drive electronics. Thank you very much. I think Stefano, you want to do a transition to how you integrated those transducers within your system, right?
Yes, right. Stefano, I'm here again. Okay, just to give you an overview of next steps. After all that effort from Maria Lisa's team and Alexander's team, we in Peralisi managed, next please, Paolo, we managed together to assemble the first machine. If you remember, as we said at the beginning, the TRL approach starts with the concept and then to the realization of a small prototype, moving then to a scaled up. This was the first prototype that we managed to assemble. We received the machine on the right with the ultrasounds, the hexagon with the ultrasounds connected from Alexander's team, and we managed the assembly of the entire machine. We built the control panel, the control logic of the temperature conditioning system of the valves, inlet and outlet valves, and we install some transducers to measure pressure, temperatures, and to manage the water flow rate and also the cooling flow rate. And at the beginning, and we managed the full assembly here in Peralisi, arriving to the final prototype, to the final first prototype. One slide back, please, Paolo. To the final first prototype built to manage a flow rate of 1,000 kilos per hour. This was the first prototype that we were able to build and send to the CITIC-SITA team in Logrogno, and so that I think Clara will be the next talking about the tests that we performed at their site after the installation within their small laboratory.
Yes, thanks a lot, Stefano. I'm Clara Olave, Marketing and Communication Manager at CITIC-SITA. Next one, please. For those of you who don't know us yet, we are a technology center located in the north of Spain and dedicated to meeting the technical and research needs of the food industry. What makes us different from another food research centers is that we work at a pilot scale. We have in our facilities different pilot plants for different food matrices, such as bakery products, meat products, fruits and vegetables, extrusion, etc. And that makes it possible for us to work with companies from the formulation to the final product, making little changes in the ingredients, in the processes, etc., so as to develop innovative products and so as to make it possible for companies to stay at the head of the ever-changing and competitive market. Next slide, please. We not only work at a pilot scale, but we also accompany companies in the way to industrialize those innovations, and that's something that we have done for Ultrasound. Our role in the project has been to validate the quality of the olive oil, and also to design the scale up of this prototype to an industrial scale. Next one, please. Well, here you can see the facilities configuration of Almazara del Ebro. We analyzed the configuration so as to, Almazara del Ebro is our industrial partner in the project, for those who don't know them yet. We analyzed the configuration of their facilities so as to assess the best way to implement the ultrasounds prototype. And we developed a flow diagram, and for that purpose, we placed the prototype between the malaxer and the decanter so the paste could pass from the malaxer to the prototype. Next slide, please. Well, once the prototype was installed and the system was checked to run properly, we made pilot tests on different types of olives. The olives were different not only from the variety perspective, but also from a maturity index point of view. And we also played with applying different intensity of power and using different numbers of transducers in those pilot tests so as to obtain different results. Yeah, the quality of the oil obtained was assessed and taking into account European legislation from a physicochemical and organoleptic point of view, and those results made it possible to compare our results to the traditional method ones. Next one. Well, here you have the microscopic imaging of the ultrasounds applied to the green olives. Here you can see the control ones, which are picture A, and then the ones to which have been ultrasounds applied, which are pictures B to D. You can see that in picture A, the walls of the cell stay intact, but when we apply more power, more intensity, the cells start to be destroyed, and thus the olive comes easily from the inside of the olive to the outside, and thus we will have a greater yield. Next one, please. Well, as you can see in the pictures, it's not only a picture, but also figures that show that the higher power applied to the olives made it possible to obtain a higher yield, and that is because in the first table, you can see that applying 60 to 100% treatments to the olives made it possible to obtain the highest yield. We analyzed the performance of the prototype, but also the quality of the olive oil obtained, and for that purpose, we considered two parameters, which were oxidative stability index and the polyphenols content. As you can see, in the control sample, the oxidative stability index is really low when compared to the one that we obtained with the ultrasounds applied, and it happens the same for the polyphenols content. We can conclude, next slide please, that we get a highest yield when the higher power is applied to the olive oil. Moreover, once the oil has been sensorially analyzed, we can conclude that this olive meets the parameters of the extra virgin quality, and moreover, the yield is really high when compared to the control one. Next one, please. Well, these are the results of the ultrasounds being applied to the changing olives, which are quite more mature than the green ones, the previous ones I was talking about. Here you can see that there's some kind of a change because the control one is the one that suffers the most. The cell breaks because of the ultrasounds being applied. And then when the olive is more mature and the intensity is higher, the cells are not that easy to be broken, and that's why you in picture D can see the cells almost intact when it comes to the ultrasounds being applied. Next slide, please. Sorry, Paolo, can you please? Yeah, thank you. Here you can see that the images were not wrong, and that when we apply the lower power to the olives when they are in an advanced, not advanced, but intermediate maturity level, we get more yield if the power is intermediate to low. Next slide, please. And you can also see that the polyphenol content is higher when the power from 16 to 50% is applied, when compared to the most aggressive treatments where the polyphenol content is lower and then the quality of the oil is not that good. But the oxidative stability index is for most of the parameters higher than in the control, so the quality of the oil is still very good. Next one, please. Well, as a conclusion for changing Arbequina olives, all the treatments increase the yield, but the quality, as I said, was quite compromised when the power was higher when compared to the lower intensity treatments. Next one, please. And here's the more mature olives, the black ones. As you can see, once again, you can see that the cells stay more intact when the power is higher. So we need to apply lower treatments, lower intensity treatments to the olives when they are more mature. And the control that you can see in picture B can be like really different. We can differentiate the cells there. So the treatment shows really improvements. Next one, please. And as I said, the more mature the olive is, the less power we need to apply so as to obtain a higher yield, and this can be seen in the highest yield that we obtain with 60 to 50% treatments when it comes to power. Next one, please. Well, regarding the polyphenol content, as you can see, there's quite a contradiction, because we have the highest polyphenol content with the highest power. So with lower yield, we got greater polyphenol content, but the quality of the oil is lower. So as I said, next slide, please. The highest yield is for the 60 to 50% treatment, and for the treatments with highest intensity, we lose that extra category. The olive oil is still good, but we could not consider that as extra virgin olive oil. Next one, please. So as a conclusion for the pilot tests, there is a minor effect of ultrasounds in empeltre and in Arbequina olives. As you could see, I've only showed results for Arbequina olives, because the effect of ultrasounds worked like really better for Arbequina olives than for empeltre, and these results will be used lately for the scale-up test, which I will be talking lately. And also the maximum power is more suitable for greener olives, as I said, with a lower rate of maturity, while the 50% power is recommended for mature olives to avoid that loss of quality that we do not want to get at all. Regarding the production capacity, the traditional process lasts 40 minutes, and we have demonstrated that lowering up that time to 10 minutes, that means a reduction of 30 minutes, is really increasing the production times and also the reducing the costs of the extraction process. Next one. Okay, so once we got all the results for the pilot tests, we went to an industrial scale in Almazara del Ebro, our industrial partner. There we installed the industrial version of the prototype, and we worked, next slide. We worked only with Arbequina olives. As I said, they work better than in Peltre. We also work with the 3 levels of maturity, but we also only applied 100% power. The only thing is that we played using different numbers of reactors so as to get different results and compared to which of them had a better result than the previous one. Next one, please. Well, the physicochemical and organoleptic analysis of the green and medium olives are still being analyzed since the campaign ended up like really some weeks ago. But the black olive tests are running this week, and indeed some of our team is in our facilities in La Rioja doing these tests. So we will have the results in the upcoming weeks, and in case anybody is interested in getting them, you can text me or anyone in the project so as to get to know more about them. Next slide. Well, we have some preliminary results of the scale-up tests when it comes to green olives from having a maturity index from 1 to 2. As you can see, the performance is really similar to the traditional one, even though we have better results for the first batch of treatments than for the second one, the one in the lighter blue that you can see. Even though they could all be considered as extra virgin olive oil. Next one, please. Yes, thank you. We have also the preliminary test results for the changing olives with a maturity index from 4 to 5 points. And as you can see, the performance here is not that good, but anyway, the levels are similar to the control one. Next one, please.
Okay, I think yeah. Clara, it's my side regarding.
Thank you.
Thank you very much. Okay, as I said, the project was planned to have a 2 years duration. We started in January 2019, and the conclusion had to be 2020, at the end of 2020. But due to COVID restriction, we had the opportunity to postpone the project 1 year, and we took this one as an opportunity to continue testing the machine. Also, we were able to build a single machine, still a 2,000 kilo machine, as the first one tested in Logroño at CTX-ITA. And due to the travel restrictions, we decided to continue the tests here in Italy, in an olive oil mill in Italy. Paolo, please, the next. And as you can see, this was a small olive oil mill, and we performed a test during the November and December periods. And we installed the Ultrasound machine in this one, and we tested both green and changing and black olives during this time. And let me show the results in the next slide about the test performed in this period. Next slide, Paolo, please. Next again. This is something confirming that can confirm what Clara was saying. We performed a test at two different temperature levels, 22 and 26 degrees, always comparing the standard malaxing time with the ultrasound application. And as we can see on the left bottom, the phenol content was comparable, even better with ultrasound at lower temperature. And also the yield was in both cases higher, as you can see on the right, applying ultrasound 2 points percentage in both cases, in both temperature levels. Next one. Regarding the sensorial results, this is still a comparison between standard, also with malaxer, and ultrasound application. The panel tests were performed at 27 degrees Celsius. As you can see, in terms of results and sensorial aspects, the two processes are comparable in all the 5 main points: fluidity, bitter, spicy, and persistency. Next. As Clara was saying, we are performing now the ultrasounds tests. But in any case, we have seen in all the tests advantages in terms of processing green olives, increasing the quality of the extra virgin quality, and a reduction in terms of industrial processing time without any effect on productivity of the process and quality of the oil obtained. But in any case, Riccardo is now at Almazzara dell'Ebro performing the last tests with the scaled up machine. As I was saying at the beginning, the scaled up machine is a 4,000 kilo machine. I think we can go to the next slide and see how it looks like in the Almazzara. Just to give you the criteria how we designed this machine, the 4,000 kilos machine is a machine built by 4,000 kilo machines in parallel. Why this approach? This approach could be an advantage in terms of industrialization, since we could have customers interested in different flow rates, and also it gives us the possibility to test the machine, the single one, at higher flow rate during the process. Also, we are pretty flexible, since the nominal flow rate for a machine is 1,000 kilo. What we are testing is, okay, if we process with a single machine 1,300 kilos or 1,700 kilos per hour, or 2,000 kilos, what are the changes in the olive oil quality, in the yield, in the processing time, and also in the overall machine consumption. And this is the reason because we have decided to have to maintain this modularity for the final machine. And as Clara was saying, we are still waiting the results since we are completing the test in this week and next one. Next, please. This is the last slide that we have. We are doing, all the partners are doing dissemination of the activity. We have started creating with the creation of Ultrasound web page, and we are continuing to disseminate the machine and the technology on different press releases. That's all. Next slide. This is the thank you for your attention. If you have any question, we are here to answer to your questions. I think it has been a long journey to arrive to this point. even if with COVID also it has been a really interesting, challenging and great teamwork, I think, for all of us. I hope to continue on this track and for the future. Thanks to all of you.
Thank you.